representing research on hateful meme detection, specifically focusing on multimodal approach to identifying harmful content that combines text and images. Hateful memes represent a significant challenge in content moderation because they often convey harmful meaning through the interplay between seemingly innocent text and images. Neither component alone may be offensive, but together they create harmful content, targeting protected groups based on attributes like race, gender, religion, or disability. Next slide. The challenge of hateful meme detection. What makes hateful meme detection particularly challenging? Unlike traditional content moderation tasks, memes require understanding both visual and textual elements simultaneously. Let me highlight four key challenges. First, the harmful content often emerges from the fusion of text and images, not from either component alone. A seemingly innocent praise can become harmful when paired with a specific image, providing context. Second, understanding many hateful memes requires cultural and social context that isn't explicitly present in the content. Models need to bridge this contextual gap. Third, non-hateful memes can have similar surfaces features to hateful ones, creating what researchers call being of confounders that test a model's true understanding. Finally, effective detection requires sophisticated visual linguistic reasoning understanding how text meaning can be transformed by visual elements and vice versa. Next slide. Dataset overview for this. This research utilizes the Facebook AI Hateful Memes Challenge dataset, which was specifically designed to benchmark multimodal understanding. The dataset includes over 10,000 multimodal examples of image text pairs with binary labels indicating whether each example is hateful or not. It's deliberately balanced to challenge AI systems with about 35% hateful and 65% non-hateful examples. Importantly, the dataset includes several types of examples. Multimodal hate, where neither text nor images alone is hateful, but the combination is benign confounders that are similar to hateful examples but are actually benign, and some case of unimodal hate where text alone signals hateful content. Next, next slide. Data preparation. Effective hateful meme detection requires careful processing of both text and image. For text processing, we use BERT tokenization to convert text to token IDs, add special tokens, pad or truncate to a fixed length, and generate attention masks. Text augmentation techniques like synonym replacement and random deletion helps improve model robustness. For image processing, we resize images to 224 into 224 pixels, convert to RGB format, and normalize using ImageNet mean and standard deviation values. Image augmentation techniques like random flips, crops, color jitter help create a more diverse training set. The implementation uses a custom PyTorch dataset class that handles both text and image processing in a single pipeline, enabling efficient batch processing during training. Model architecture. This research implements several approaches to hateful meme detection with best performing architecture using cross-model attention. Let me walk you through these approaches in different increasing sophistications. Firstly, we have unimodals. First, we have unimodals using BERT and image only using ResNet. These serve as important baselines but fail to capture the multimodal nature of the hateful memes. Next, early fusion. Simply, simply concatenates text and image features before classification. It's straightforward but does not capture complex interactions between modalities. Late fusion process text and image separately, then combines predictions. This perform better than unimodal approaches but still misses nonce interactions. Finally, our best performing approach uses cross-modal attention, which dynamically attends between the image regions and text tokens. This captures the nonce interaction between modalities that are essential for understanding hateful memes. The cross-modal attention architecture follows have five key steps. Process the image with ResNet 50 to extract visual features. Process the text with BERT to extract textual features. Apply cross attention between visual and textual features. Generate a unified multimodal representation. Feed this representation into classification head for binary prediction. Training implementation. Next, the code training. Yeah, training. This research implements a comprehensive training pipeline with the following configuration. We use a batch size of 32, a learning rate of 2 to 10 power minus 5 with ADAM VW optimizer, a linear learning rate scheduler with warm-up. Training runs for 10 epochs with early stopping based on validation performance. Binary cross-entropy serves or loss function with ROC area under the receiver operating characteristic curve as a primary evaluation metric. Several implementation considerations proved important for effective training. Used pre-trained models, saved the compute resources, and improved performance. Handling class imbalance was crucial given, given the dataset 35 by 65 split. Careful validation prevented overfitting to training data. Gradient clipping helped stabilize bird fight tuning. Learning rate warm-up improved convergence with transformers. This is a code for the implementations. Here are the results. Our research compared several approaches to hateful meme detection, demonstrating the superiority of the multimodal methods. Performance results measured by RX score are text only, BERT text only 0.65, image only 0.59, diffusion 0.71, 0.71, late fusion 0.73, cross model attention with 0.77. These results clearly demonstrate three key insights. Multi-modal consistently outperform unimodal ones by at least 6 percentage points. The most sophisticated cross-modal architecture achieves a 12 percentage point gain over text-only systems. The gap between unimodal multimodal increases on more challenging examples. Let's go to error analysis. Analysis of model errors reveals several patterns. False negatives, 60% of errors occur with more frequently than false positives, 40%. With models struggling most on examples requiring cultural context and those subtle hate speech with implicit references. These research identify four particular challenges example types. Implicit associations between seemingly neutral text and codal visual elements. Benign confounders similar to hateful content, but actually benign. Contextual subversion, where the image changes the meaning of the text. Adversarial examples deliberately designed to evade detection. These techniques can be applied to several real-world use cases, including content moderation on social platforms, hate speech research, platform safety systems, and social media monitoring applications. In, in conclusion, this research demonstrates that multimodal understanding is essential for hateful meme detection, with cross-modal attention providing the best performance by dynamically connecting relevant parts of the text with specific image regions. While significant progress had been made, challenges remaining at detection, implicit hatred, understanding cultural context, and handling of the adversarial examples. Future work in this area should focus on incorporate border control text, developing more robust models against adversarial attacks, building explainable systems, and reducing computational requirements for development in resource-constrained environment. Thank you for your attention. I'm happy to answer any questions in this research. That's it.